Greetings and peace from throughout the boundless universe. How y'all doing today on this shadow? I'm glad to see y'all in the house. I will be in the house. Peace. I decided this shadow hour that we would talk about this video. And I wanted to talk about zero. And the video is called, let me see what the name of the video is first. Not that one. Let me see. I was going to do this zero even.
Zero.
But not that one.
Yes. To a mathematician, this is a number. But
we're going to do another one. But it's going to be based on zero.
The Catholic Church.
Yeah, we're going to do is zero even. So we just kind of stall and letting people get on. But we're going to do a video called Is Zero Even? So it's going to be a very good video. It's going to tell you a lot of stuff. It's going to relate to the number new. If you haven't been here before, this video, zero divided by zero, is going to relate to this number right here. See this number right here? The number right there is called new. N-U. Okay? We ain't talking about the zero. We're talking about this number right here. New. And then this number right here, 0, 1, or 0 new, or 0 new, or 0, 1, 0, 1. That number right there is called UN, un, or UN, un. So it's just like un, new, un, new, un. So then you would get like 0, new, new, and you get that right there. So that would be an on, new, on. So these are new numbers on the number line and in mathematics. So with these new numbers, and I'll tell you something. In many videos, they'll talk about new numbers, but what they're talking about is huge numbers. They're just saying like, I went from, like for instance with Bitcoin. They use a number called a quindecillion. Now, that's a huge number. I agree. That's a huge number. And it'll take a long time to figure anything with that number. But with the right computer, you could. So making large numbers, it don't mean nothing. It's not really encryption. It's no better encryption than that than actually using what's already in place, prime numbers. That's the truth. So now, but on, new, on. That's our numbers, y'all. And remember that our mathematics, just for a reminder. I know y'all might say, golly, I heard that before. But some of y'all might say, no, I didn't. I didn't never hear it before. I didn't never hear the brother and his mate teach on that before. Peace, BASTET. Okay? So this word, my, well, actually, I ain't gonna like this, but I gotta do it. We'll do it that way. Okay? So then we'll put a period between here, just so you'll know that that's an abbreviation for something. Now, this abbreviation is for, we want to do two of them. So we'll say minus. It's for minus. This A is for alienate. Alienate. And this A is for add. And this T is for time. Okay? So now, this abbreviation in our mathematics, this abbreviation it represents minus, which is subtraction, alienate, which is division. So you get your subtraction, your division, your addition, which is add, and times, which is multiplication. So you get these four. And this is the order of my eye. This is the actual order. Like they have PEMDAS, so please excuse my different. No, we have a new order of operation. It's minus, division, plus, and times. We also have order, which is an additional letter onto my I. O, and it stands for order of operation. And it stands for the order of operation. Sorry about that. Okay, so it stands for O, order of operation. And so this order of operations would be equivalent to your parentheses and your exponents. It would be equivalent to your parentheses and your exponents. I ain't gonna write the word out, I just do that. Your parentheses and your exponents. That's how we write exponents sometimes. When something to the power of something, we just write an arrow. So it'll be a reference to your parentheses and your exponents. So P would be your parentheses and E would be your exponents. So this represents that, but this also represents something else. So we really don't call it this right here. That's why we call it orders, because it also represents something called the equalization. It represents, we'll call it EQ, just for the sake of we have an E up there and a P there. So we'll call it EQ, which is equalization. But these equalizations act like parentheses as well as exponents in this order of operations at this point. So as they would have this parentheses and exponents at the beginning, we cover them at the end. Where they have it at the beginning, we do it at the end. So where they would have, let's say, parentheses, exponents, then they have multiplication, division, addition under P, right? And subtraction under E. So they will have PEMDAS. So they will have something like that. And so then they will have the P at the beginning where we have minus. They will have the exponents right here where we have the alienation parentheses where we have minus, exponents where we have alienation, multiplication where we have add, division where we have times, addition where we have parentheses, and subtraction where we have exponents. And they don't hold a spot for equalization. They don't hold a spot. This is a new form of mathematics, equalization. It's a form of the mathematics when we say peace and love you, thank you for the big ups. When we mention aesthetics, when I say aesthetics, I'm saying, I might as well be saying EQ, equalization. Because equalizations are where you take something that's been superimposed and superpositioned and supersymmetry, and then you take it and you understand, you comprehend that supersymmetry and all of them together till you get to the point where you have an equalization. It's almost like saying a grand total, but it's not the grand total. It's an equalization of the numbers. Okay, it's a balance. Okay, so equalizations. So that's something that they don't have in current modern day mathematics, that new mathematics will be added. So that's an EQ, and it's called equalization. So this order right here would be called E, Q, U, A, L, I, Z, A, T, I, O, N, S. Equalization. That would be what this really is. So that would take the place of parentheses and exponents. Now let's erase this, because I don't even like that up there. That's too much of a reminder of what ain't to be. Okay, so now, Let me see. How do we go from here? Okay, so now I want to tell you this. This M, it also stands for mind. Mind. And M stands for mind. And then this A, alienate for division, it also stands for ancient. Y'all get that? Y'all got that? I didn't quite get it. Let me come up some. Make sure everybody can see. It stands for ancient. Ancient. And so then you have here, let me draw a line there so I won't go below that color. And so then you have my ancient, and then you have addition. So then you have her ancestor. So this is, we actually writing out the acronym for Ma'at. Oh, Ma'at order, or Ma'at order of operation. We're actually writing that out. My ancient ancestors taught. That's going to be the T for taught. Taught, and then for the O, we would say order. My ancient ancestors taught. And then right here, like we have this sign, and let's say we would put a sign like this right here. Or let's erase this right there. For red. And then so like we have this minus sign, like we have the alienate sign or alienation sign, like we have this add sign, and like we have this time symbol or sign, then we should have a symbol for the order of operation, which we have yet to actually create. So right now, that symbol is being held by this spot, but somebody can actually help us create a symbol for the order of operation. Somebody can actually help us create a new symbol for the order of operation. If they wanted to help us create a new symbol, we have a new symbol for the order of operation. And so, so minus, alienate, add, times, order of operations. So this would be order. So this order is directly related to the verb aesthetics when we talk about we are indigenous aesthetics, mathematics, and linguistics. When we say that, when we say we are indigenous aesthetics, mathematics, and linguistics, I'm going to erase this, y'all, the order of operations, my order. I hope that I got that. Yeah. So let's see how we can do this. So we say we are let's do it in all caps. Indigenous aesthetic mathematics, and you can say linguistics. Indigenous aesthetic, mathematics, and linguistics. And so when we talk about order, that's in direct relationship to the aesthetics. When we're talking about the mathematics, that's in direct relationship to the number line, new numbers, the new order of operations itself, not just the order, but the whole new order of operations itself, and the new solutions to problems. So when we say mathematics, we basically talk about new and on. These two numbers right here, new and on. And so when we say linguistics, we're basically talking about the fact that not only do we introduce numbers linguistically, because we like to point that out, but when we talk about linguistics, we're talking about the fact that mathematics itself is a universal language. Now, that's like a corny term because people use it and don't really know what it means, like power in numbers, or like the math don't lie, things like that. But mathematics, linguistics, actually, you know, how can I say it? Mathematics is a language. When you write down the symbol, you're speaking in a language. And that language is in signs and symbols, but not called numbers and numerals and addition signs and things like that. But it's nonetheless, it's a language. So when we talk about linguistics, we're talking about the whole branch of linguistics and mathematics, from the historical point of view, from the etymological point of view, from the archaeological, paleontological, if you will, just in paleontology, just in every way. So when we say linguistics, in the beginning, what's the word? We talking about the very numerals, numeric, and number. That's really what we're talking about. We're talking about the whole thing, about the numerals, but numerals are different than numerics. And that's different than numbers, okay? Because numerals deal with the language of the thing. The numerics deals with the numbering of the thing. And numbers deals with the actual number itself and the value by the sum. So these are three totally different things. And that's what linguistics does. It breaks things down like that. Okay? And then when we talk about indigenous, our indigenous is for the simple fact that everything we teach, let's write that in our caps, is all native. Everything we teach is native. Everything we teach is native. We teach nothing that is not native. Everything we teach is native. Native Egyptian, native, if you will, Nubian native, because we cannot say that word. We would not say Native American, because we know it's a lie. We got to change that, so we have to learn the truth. It's Nubian native. So the Nubian natives, these people, we are all about that type of indigenous matter. And no matter where those Nubian natives reside on this planet, indigenously, we're about that matter. So that's basically what the breakdown of indigenous aesthetics, mathematics, and linguistics is. Now, we could go into the next part of it, but this is the part that I want you to know. I want you to know this in the simple order first, that indigenous relates to native. It relates to native mathematics, native culture, native. It relates to native culture, and now I'm going to have to add it in. It relates to native culture, native ceremony, native civilization, okay? That's a little bit native civilization and community. And so this right here, we're gonna have to go ahead on and add this fourth one, and we'll put number line. Okay? And that'll be basically what we have. These four N's: numerals, numerics, numbers, and number lines. Those are different things. Number lines will include graph lines. Okay? And then you have culture, ceremony, civilization, and community. And I added this one because we as natives, we always teach in fours. So in linguistics, as indigenous people, teaching linguistics, we teach linguistics in fours. As indigenous people, teaching mathematics, we teach mathematics in fours. So this would be new, on, and then you would also have 1 and 0. So that would be 4. And then here you will have culture, ceremony, civilization, and community. And here you get a whole bunch of stuff going on. But just remember, we said it's parentheses going on here, it's exponents going on here, and it's equalization going on here. And those three for the order of operations. Those three equal that. So that's 4. 1, 2, 3. So in aesthetic mathematics, in indigenous mathematics, as native people, we teach in fours: culture, ceremony, civilization, and community. As indigenous people, we teach aesthetics in order, parentheses, exponents, equalization, equity. As indigenous people, we teach mathematics in fours: new, on, 1, 0. New, on, -1, -1, 0, 0, 0. As indigenous people, we teach linguistics in fours: numerals, numerics, numbers, and number lines. This is what indigenous aesthetic mathematics is all about. This is how, if your child came to one of our classes, this is how your child would learn. Your child would learn indigenous, native, culture, ceremony, civilization, and community. Your child would learn aesthetics, order, parentheses, exponents, and equalization, dealing with the order of operation: minus, alienate, and time. So they'll learn a new order of operation, and that'll be a part of the order. And they'll learn the order of equalizations and parentheses and exponents at the same time. They'll learn in this mathematics, and that's the aesthetic part. In the mathematics part, they'll learn about new and on, new, and 0, new, and 0, new is on, or 0, 1, and 0, 1 is on, a 0, 1, a 0, 1 is on, a 0, 2, a 0, 3, a 0, 4, 0, any number is on. Okay? So then that's the linguistics. So in there, that's the mathematics. And so, and the mathematics of that, let me show you some of the mathematics of this new and on. Let me show you. Because new and on, new is the real identity of 1, and on is the real identity of 0. And so you have basically 4 operations, and they go in this order. So you can write this order down, and you can never be lost on this order. This is a new order. This also is a new order that has never been explained to you, except for via new mathematics. So the order of operations, and then the equalizations, the order of equalization, and then now we have this order of the operations. When we say order of operations, we explain operations within operations. Within the order of operations of my, within this order of operations of we'll say within the operation of minus, alienate, add, and time. Within those operations, we're going to show something about this operation, but we're only going to deal with this operation right here. But this operation will apply universally to all the other operations. So what I want to show you is that when we deal with the mathematics of this, then what we mean is this right here. 0, This is something you know. 0 divided by n, 0 alienate n equals 0. That's something you know. Now, the next operation would be 0 divided by 0 equals. Now, that's something you don't know. Not the answer, but the fact that this number is this equation or this operation with solution, this operation solution, and the word solution can be written over here as well. So we'll write that as O, because solutions are found over here as well. So 0 over n equals 0. 0 over n equals 0, or 0 alienate n equals 0. But what you didn't know is that this actually follows this. And this is what your children will learn. This will help them develop their mathematics, their thinking skills, the order of arrangement of the mind, the order of arrangement of thoughts, the order of arrangement of the mind, the order of arrangement of the connection to the mental. All of this can be reestablished by having an established brain. If we establish something here, then it automatically relates to the mind, and it automatically relates to the mental. So we have to be willing to establish something in the brain. And what we want to establish in the brain, get the brain to see or get the brain to recognize, is that, hold up, it's the other stuff that you can't see, like this, like 0 alienate n equals 0. That's important, but we know that. Now, what we don't think about is, how big is that? How big is 0 divided by 0 alienate n equals 0? How big is that? How big is n? So that means we're taking this much out and making 0. So how big is n? So in a way, this 0 is as big as n. I'm going to say it again. In a way, this 0 is as big as n. If you're going to alienate n, which means to alienate n, then you're left with this 0. This n is n0. This n is n0. Okay? I just want to explain that to you, because these things don't get explained to children. It gets thought about as if this just disappears because you said 0 divided by 0, as if this n just goes somewhere. But your debt don't go nowhere. Debt don't go nowhere. It's minus. It don't go nowhere though. It can go to a collector and earn interest. You see that? So no. 0 divided 0 alienate n equals 0. That's known. But what follows is not known. What this amount is not known. So these are the things that I want you to see that IML, Indigenous Aesthetic Mathematics and Linguistics, IML, IAML, really, what we teach. So now, 0 divided by 0 equals this new number right here. Now, before we move any further, let's go back to 0 alienate n equals 0. Let's pick a number n. Let's say n will be 1. And so we will say 0 alienate 1 is always 0. 0 alienate 2 is always 0. Now this is what you should show your children, because they'll understand a lot by dividing by 0 and seeing the activity of 0 in the part that you do know on the number line. 0 alienate n equals 0. They can find that in the calculator. They'll find a teacher teaching that. They'll find you teaching that. So they'll be secure with knowing that. That's built into the genetics right now. But what we're going to establish is something else in the code. Okay? But until then, let's talk about this. Let's talk about just the regular use of a number line, and the use of a number line that you're not used to. Like, we're used to just hearing 0, 1, 2, 3, 4, and we don't even hear 0 really. We're 1, 2, 3, 4, 5, and 5, 4, 3, 2, 1, and then that's it. And then that becomes the number line. And when you get a little bit older, they go 1, 0, -1, 2, 3, 4, 5, and then they explain a little bit about negative numbers. But they show you how to add, subtract, multiply, divide, all those numbers down here, away from the number line. They show you how to divide away from the number line. 3 divided by 3, or 3 divided by 3, or 3 divided by 3. So then this becomes the confusion, the divided. This becomes the confusion, because first, you haven't even given me a definition for what divide means. What is divide? What is divide? See, that should be a dictionary, which IAML has. That should be a dictionary, definitionary for the child on the mathematics that's within the book. We don't call it a definitionary no more, though. We call it just linguistics and lingo. So when you check out the lingo section of a book, you will find words that relate to the mathematics that will tell the child exactly what the word is. It does not diction the word, pronounce the word. It explains what the word is in mathematics, what the action is, what the word does in mathematics. That's what IAML has the ability to do. So what I want to show you is on this number line, let's just say 0, whichever sign you want to put here, divided by 1 equals 0. 0, put that sign there. 0 divided by 2 equals 0. 0, we can use that symbol. Divided by 3 equals 0. 0, so on and so forth. So those are the 4 symbols of division. And so, but what takes place is you basically can show the division by 0 on the number. 0 divided by 1 equals 0, son or daughter. 0 divided by 2 equals 0, son or daughter. 0 divided by 3 equals 0. 0 divided by -1 is still 0. 0 divided by -2 is still 0. 0 divided by -3 is still 0. Anything divided by 0 equals 0. 0 divided by anything equals 0. I apologize. 0 divided by anything equals 0. Let's say that again. 0 divided by anything equals 0. So 0 divided by 1 equals 0. 0 divided by anything, or anything, infinity. 0, let's do it. 0 divided by infinity equals 0. 0 divided by anything equals 0. So even infinity divided by 0 equals 0. 0 divided by infinity equals 0. So now, I'm so ready to get to 0 divided by 0. That's my problem, y'all. This is what we teach on. So I wound up saying 0 divided by infinity when this is, I wound up saying infinity divided by 0 when this is 0 divided by infinity, or 0 alienated infinity equals 0. But nonetheless, your child will be happy and elated to know that they can even divide by infinity. They are dividing by infinity. Just like we're going to divide by 0, this is dividing by infinity. So they can divide by 0 and divide by infinity. And come up with an answer. And know that the answer is correct. Know that infinity is no longer something they can't reach. Now, but what if 0 divided by 0? Now, where would you get this number from on your number line? 0 divided by 0 divided by 0 divided by. So it's no other 0. So this can't even be a number. According to your number line, this and this can't even exist because you only got one of each. You only got 2 of those. So you can't have 0 divided by 0. So where are you going to get the other 0? Because you only got 1 0. So now, what you have to do is, you have to step up your game to this number line. And when you do that, you have 2 zeros. And by the way, this 0 is not really negative, but it's important that we have it here because it's on the negative polarity. And because it's along the negative polarity, the solutions along this negative side are different. They contain negative results. And because we will perform action on this negative side, this negative sign will be helpful. We use numbers like and new later on in mathematics. So that's going to be helpful. So now, But just remember, this zero is not really negative. This is zero just like this zero, just like this zero. But these zeros do have different features and different quantities. So just remember that a thing can be equal, but not equivalent. They can be equal, but not the same. Like 5 plus 5 equals 10. These are equal. This equals that, but they are not the same. This is 5 plus 5, and that is 10. So they can be equal, but not the same. So that's another secret in quantum mechanics, physics, and computing and processing that we're going to reveal. The equal and not the same is very important. A very important construct, not a concept, a construct that's built into the mathematics of quantum that you have to understand, because it's what the numbers, peace and love, peace. Thank you. Now, 0 divided by 0 equals nu. So now, we said we're going to have to step up. Let's step up to nu, and well, we got 0 divided by 0. In fact, we have the division line. In fact, we have basically this answer. 0 divided by 0, 0 alienate 0 equals nu. That's the answer right there. 0 alienate 0 equals nu. Or you can say 0 alienate 0, and that equals nu. So when we write this, that's part of the language of mathematics, where the symbols actually become the numerals, actually become a part of the numerics and the numbers, and the number line. The number line actually becomes a part. What I mean by a number line becomes a part, suppose this is a graph, and I want it -4, -3, -2, -1, -0, and nu. Nu would be on that line. So the number line actually becomes a part of the mathematics. And this line is like this line, and this line is like this line. So all of these lines are equal, yet they're not the same. But this number is a result of division. See, this number results from 0 divided by 0, or 0 alienate 0 equals nu. So these are the things that will be explained. This is the language of mathematics. And so when your child hears this, your child can relate to the number 0. Don't judge it by what you think either. That's not fair. Give your own child a chance to see, because the things you can see are not what they see, and you can't see it into the world that they exist in. And you know that in our, because we're now adults, we're now mature, and we remember when we were children how vast the mind was, how creative, and how plastic and fluid, and how elastic, and how rubber the mind was, how the mind could bend. And now it's become rigid over time with different teaching. 2, 3, 4. So you see how this can become a part of the number line, and this is part of the linguistics and aesthetics. See, this is what makes it indigenous, because this is ancient. This is what makes it aesthetic, because this is beautiful. To know that, to realize that. And then even here, 0 divided by 0. 0 divided by 0. 0 divided by 0. You see that? And it all equals nu. And that number just stays the same. So it's the singularity. You see that? So that's why it's called the singularity. That's why it's called a pole. It does not move. Okay? So now, we have this. And I'm telling you, whether you know it or not, I love y'all, but we have to say this, y'all. I'm telling you that we need your help and your support in donations. Please help us out. Help us keep going with the videos. Help us keep the internet on. Come on now. We pay for the internet. We pay for cable, light bills, you know. So help us out, man, for real. It ain't even funny. But help us out just like you support the other people and the other people that do what they do to contribute to the community. Let this be our contribution to the community, our way of giving back, and y'all give us so we can continue to give. That's all we ask. So then we have 0, the alienate 0 equals new. And so now this is where a number like infinity becomes important, because let's say we replace new with infinity or 0 with infinity, it really wouldn't change nothing, because we got those numbers coming up. Infinity over infinity, that's n and n. You know, 0 over infinity, we got that. Now infinity above 0, that's over there, alienate 0. And then there's no other combination for that other than with an interaction between infinity and new. An interaction between infinity and new might be interesting. That might be an interesting combination, but it wouldn't be that interesting, because anything's going to be the number when it comes to new, because new is the identity. So now, let's do this. So 0 divided by 0 equals new. And we showed you that in the number line. We showed you that 0 alienate n. 0 alienate 1 equals 0. 0 alienate 2 equals 0. 0 alienate 3 equals 0. 0 alienate 4 equals 0. So like that. So then, 0 alienate infinity equals 0. So then 0 alienate 0. 0 alienate 0. The child will have a problem if they just saw this number line. It's just like 0 alienate 0. 0 alienate 0. What could he mean? What could she mean? 0 alienate 0. 0 divide 0. What could you mean? If I only got one 0, how would I divide by 0? I got to create a mystery 0. And then when I look at the number line, when I look at the graph line, I see this. -4, -3, -2, -1, 0, 1, 2, 3, 4. And I see 0 on the line. So I said, well, what is that? What is that? 0 on the line. Well, if I look real close, I would see this at least. I'll see new. I'll see new going through 0. I'll see new just like this. I'll see new right on that 0. I'll see new just like that. I'll see the 0 is not alone. I know something else is on this line. I know it's another number exists on that line, and that number is new, and 0 is on top of that number, like a 10, like the number on, like the number which we about to get to. I just want to paint the picture for you. That 0 is sitting on this line, and what you didn't see, what you had to see, what you got to show your child is that I right there. What that 0 is look through that 0. And what's behind that 0? There's something behind that 0. And that's the line, that's the pole, that's the singularity. Okay? So now, and when we get into quantum, that's when we're going to scoop that 0 up, and we're going to scoop that 0 up to the middle of that line. And that 0 is going to be on all 4 corners. And that 0 is going to be like a target. And then we're going to be working with some real numbers. So these are the number lines that you will be introduced to in indigenous, aesthetic, mathematics, and linguistics. This is not a joke, folks. This is the real deal. This is real mathematics. This is the truth being put forth to you so that you'll gravitate towards it and accept it and allow us, by helping us, to make it acceptable and presentable. This is not presentable. Allow us to make it presentable. I'll show you a video of somebody who's making it look presentable, making their stuff look presentable. So now, let's look at this. So once we move from here, okay, I'm going to leave this, but I don't want to be confused because we like aesthetics. So we kind of missing something here. So for the sake of it, we're just going to say new. No, for the sake of it, we're going to say infinity. Divided by infinity equals new. That's how we'll do that. That's a good one. That's very aesthetic. So now we can move on. So now, our next number, again, is going to be any number. That's what n represents. Any number And we can make that n infinity. We can make this n infinity. Any number. Any number. So any number is not infinity. Any number is any number, but any number goes up to infinity. So any number, now we can say it finally again, divided by 0. Any number divided by 0. So now, let's be clear. N is in the denominator, 0 is in the numerator. 0 is in the denominator, 0 is in the numerator. 0 is in the denominator, n is in the numerator. So this is n alienate 0, this is 0 alienate 0, and this is 0 alienate n. And so n alienate 0 is going to equal this number here. 0 any number. It equals that. 0 any number. That's what it equals. N alienate 0 equals 0 any number. Just take that number. And so that's our next property. That's our next property. So then our next one that we'll want to put over there, we'll use infinity. Infinity. Alienate 0. Infinity alienate 0. Now what's that answer going to be? We already know. We can look right there. What's the answer going to be? The answer is going to be 0, infinity. That's the answer. 0, infinity. Let's do that a little bit better, since people like infinity so much. Okay, 0, infinity. So you see that? That's what we'll have. And then we have this function. Now, I don't want you to get lost. I want you to still be with me. I want y'all to stay with me. Because remember, out of everything we showing, with the little fan out at the bottom, what we're really showing is that this comes first in the order. This comes second in the order. This comes third in the order. And the next comes fourth in the order. Just like this. But this is different than this. Minus comes first in the order. Division comes second in the order. Alienation comes second in the order. Add comes third in the order. And times comes fourth in the order. So this is M-A-A-T. That's my right there. We got that. So that's one order. But this is an order within division itself. This is an order within division itself. And we could create this type of order in subtraction, in addition, and multiplication. So therefore, IML, New Mathematics, we have developed, I just erased number line, and graph line, number lines and graph lines, but we have developed a whole new system of mathematics. All I can tell you. It's really difficult to explain what I was about to try to write. But this is only orders within the order. This is all I can tell you right now. Those are only orders within the orders. We have many different orders of operations that we can show you. Even when you transfer from this number line to this number line, this order flips. This order actually transposes itself, and subtraction or minus and add, they actually flip like this. They actually change places. And it becomes am. So these actually flip and reverse in polarity because it's like a helix. Maybe you can see this, the numbers going straight up parallel, and then all of a sudden you reach 0 divided by 0, and all of a sudden you get this new number called nu and on. And the numbers do like this. And they'll go up on opposite sides, just like your optic nerve and your sight line. They do that. The numbers do that. That's how numbers operate. That's why I call the orders of operations, because they have an operation to perform. They don't just go straight up in a line across the paper. They make circles and everything. Numbers form shapes. I think I showed y'all this. Let me show you. Well, we showed the circle. We showed this circle where the numbers actually form the square. Where those numbers actually form the square. Where these numbers right here actually form the square. I'll show you. See that? They actually form that square right there. So that was some very powerful mathematics, because that's the first time in the history of the world you ever seen the squaring of the circle or the circling of the square. That's the first time. You can Google that and you'll see nobody on the planet can do that. Google that. Google circle in the square, square in the circle, and you'll see nobody on the planet can do that. Nobody on the planet can do that. And the reason why I say nobody on the planet can do that is because I want my people to recognize who we are and what we do and what we bring to the table. Not for braggadociousness. No way, that ain't me. I'm saying because we have a job to do, and I'm looking for the right people. So now let me show you this. I'm just looking through some papers. I had a pretty little drawing though, more aesthetic for the children that I thought would better fit that purpose. Let me see. Oh, right here. Yes. Right here. So take a look at this. See that? All praise is due to the Most High. See that? I'm going to bring it closer so you can get the bottom. And then I'm going to bring it down while it's still close so you can sort of get the top. And so that's the beauty and aesthetics of mathematics. That's the beauty and aesthetics of mathematics. You see a lot of stuff going on. That's not just no joke that we actually have, operations with new and on within that framework. So that's a very high level of mathematics. And so then you have n divided by 0. Let's start from the beginning, y'all. We have 0, alienate n equals 0. We have 0, alienate 0 equals nu. We have n, alienate 0 equals 1. Or this number, 0 n, like this number is pronounced nu, n, u. This number is pronounced u, n. Both of these numbers appear undefined in your calculator and in your computer. Both of them. Indeterminate, error. So now, the next number we'll do is n divided by n equals 1. Any number alienate the same number equals, alienate any number alienate itself or the same number equals 1. So now, notice that this equals 1 and this equals nu. 0 alienate 0 equals nu. 0 alienate 0 equals nu. But n alienate n equals 1. You see that? N, 5, right? 5. Alienate 5. If these are 2 5s, not negative 5, but 5 alienate 5 will equal 4 alienate 4 will equal 3 alienate 3 will equal. So these will equal nu. Just like, but nu wouldn't be in its identity as nu. Nu would change its identity and nu would call itself 1. Nu would call itself 1. Because nu has other identity. Because n times n equals n squared. So then if that was 1 times 1, that would be 1 squared. So then this 1 squared is equal to that 1, just like this 1 is equal to nu. But they're not the same number. Nu is here, 1 is here, and 1 squared is whatever you square. whatever number you square is that number. So now, let's see. So let's erase this multiplication right here at inverse. And we already used up our infinity over infinity. So the only thing we can use down here is if we say new, this would be interesting. New divided by 1. And the answer would be 1. Even if it was reversed, if it was 1, alienate new, it would still equal 1. Because new is the identity. New actually does not appear along here. So new just has 1 as an appearance. It has 1 to make its appearance. But new remains as the polarity, the pole, the similarity. I wish I was here so I could say just that makes sense. Okay, so now, let me see. So that's what indigenous aesthetic mathematics and linguistics really is all about. The foundation and fundamentals, the basics of mathematics. We're into the research and development of that. And we need your help and your assistance to help us research and develop them. The fundamentals and the foundations of this mathematics. You see, we have that already intact, but we would like to put together a curriculum, a textbook, different things like that, a number line, graph line, with the real mathematics on it, not just bits and pieces, but the real mathematics. And so, we have I didn't even say that. We have our own, by the way, we have our own subtraction table, alienation or division table, add or addition table, and times or multiplication table. We have a table with all of these, not just a multiplication table. All you have is a times table. That's it. But suppose there is an addition table, a division table, and a subtraction table. Suppose that minus, alienate, add, time. Suppose all of them have their own table that you can put in place. Okay? So that's the kind of thing that new mathematics will bring to the table, that we're able to put together something as vast and huge of a job as that, to put together those tables, which we already have together. We already have them found. So you don't even have to go out and try to do nothing, try to make nothing. Just order it from us and allow us to, do what we do. Because the one you make couldn't be the one we have. And it wouldn't operate the one we have, like the one we have. So please, just help us out. So, we'll erase that. So that's a little bit about indigenous aesthetic mathematics and linguistics. That's a little bit about us and about what we teach. We teach indigenous native. That pertains to the order. We teach indigenous aesthetics. We teach indigenous mathematics. And we teach indigenous linguistics. And we teach that that's my. We teach that all of that is my. And so, wait, before we go, it's always good to do this. No matter how many times we do it, it's always good to do this. Culture, ceremony, civilization, and community, that's good. Okay. So now, let's see. Let's get rid of this. Okay. Now, let's just check it for the inverse. 0 times n equals 0. Fact. New times 0 equals 0. Fact. On 0 in times 0 will leave us in. Equals in. Facts. N, alienate N, equals nu. So 1 times N equals N. Facts. Fact, 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 fact. On the alienation level of division, 0 alienate N equals 0, fact. 0 alienate 0, nu, fact. N alienate 0, on, fact. N alienate N equals 1, fact. 0 times N equals 0, fact. 1 times 0 equals 0, nu times 0 equals 0, fact. On times 0 equals nu, equal N, fact. 1 times N equals N, fact. So then, that's the check. That's the reverse inverse. Check. So we can check that mathematics and everything out. Now you can check it out at home. You can go at your house and you can put any number over 0, any number alienate 0, and then you can make that number, let's just say 19, alienate 0. Then this number will be 0, 1. Let's write that 1 like this. Gotta remember that. Got so many bumps on the 1, and then this. And if this number was so this would be 581 on. Say that with me. 581 on. 581 on. And if we brought back our 19, that would be 19 alienate 0. That would be 19. That would be 19 on. 19 on. 581 on. So that's how that would work. So any number we put up there would be on. So like we said, just for the record, infinity, infinity. Infinity on times 0 equals infinity. 19 times 0 equals 19. Facts. So you now know how to use 0 in the denominator and how to divide by 0. You now know how to use 0 in the denominator as well as in the numerator and divide 0 or 0 alienate 0. And now you know what it equals, the number, nu. Now you know what n alienate 0 equals, 0 n, on. Now you know that nu is the real identity of 1. Now you know that on is the real identity, on is the real identity of 0. Now you know new numbers, that's 0, that's 1. Now you know new numbers, new number line, new solutions to problems, new solutions. And let's put this on record. We just can't say new solutions to problems. We just can't do that. This is new solutions to unsolved and unknown, unsolved problems. unknown answers though. And you have learned. Let's go ahead and throw graph lines in here, okay? And graph lines, because you got graph lines too. You have, along with numbers now, you do have new numerics, new numerals, right? Along with the number line. And then you have new orders of operations. And we taught the new orders of operations by saying this comes first, this comes second, this comes third, and this comes fourth. We taught that this is an order. We taught that that was an order. Minus, alienate, add, times, order of operations. My ancient ancestors taught order. We taught that that was an order. We taught that that's order. So this is one order of operation. This is a totally separate order of operation. And we showed another order of operation. And we'll show many more in the future. So don't worry about it. But I just want you to see what we have been able to teach, remind you of in such a short period of time, just right here on this broadcast, right here on this live stream. Just right there, you know, these are the secrets of the universe. Right there, how to divide by infinity, using infinity with numbers, dividing by zero, using zero in the numerator and denominator. The truth, you learn a new identity. Of 1 and 0. See? So it's a lot of things. You've learned about this and this on. You've learned about -0 and +0. You've learned about this number nu being the pole on the graph line. You've learned about 0 on the pole of the graph line. You've learned a lot about what happens in new mathematics. You have great tools to go off of. You have a great foundation and a great base for the fundamentals of what new is and how it manifests. New is produced along the lines of division. On is produced along the lines of division. We see that. You can see that. You can see this order of division. So you know that division ranks very high on the scale or the orders. So that's why I said these orders equal equalizations, but you have scalar, C-S-C-A-L-A-R, and then you have orders of magnitude. You see what I'm saying? So this level of orders over here, just imagine what would happen over here if you take everything minus, everything alienated, everything add, everything times, everything parentheses, exponents, brackets, everything that's equalization, magnitude, scalar, and then you come up with an equation for this. Then that's what we'll be talking about. That's what we're talking about. So, let me see. So, and that's just some of what we got to teach around here. That's just some of the things. And we've shown this on other videos, but we have to point out what we are teaching for those who are new, and especially to do a recap for people that really have to, really get into their numbers. There's numbers, okay, new number lines and graph lines, new solutions to unsolved problems, new orders of operations, new identity of 1 and 0, the order of my I, O, everything explained, new graph lines along with those number lines. And then so we won't go into this. However, we'll do a short synopsis. 0 alienate n equals 0. So let's do the inverse. 0, because we did the reverse inverse. We said nu times 0 equals 0. That's the reverse inverse. But now we're just going to do the inverse. That was the reverse inverse, performs a check. Write that down. Say the reverse inverse is the check. The reverse inverse is how we check. Reverse inverse is how we check. Now, how do we inverse though? Invert this. So then, it don't mean to turn it upside down really. It means to change the sign from alienate to division. So to division. I'm sorry, from alienate, change it to multiplication. I apologize. 0 times n equals 0. That will check out. That will check out. 0 times n equals 0. Facts. No, hold up, sorry. I forgot. I might be writing slow. 0 times n equals 0. Yeah, come on, Jack. Okay, now, so then let's just do the inverse of this. 0 times 0 equals 0 squared. Wow, it does not equal 0. It equals 0 squared. Because the number multiplied by itself, or a number times itself, equals a square. So this number is 0 and 2. So this is not this 0. Nope. And it's not this 0. So what 0 is that? That's its own 0. It's 0 squared. Just like 1 and 1 squared. Then 0 squared and 0 are not the same. So now, let's do the inverse of this one. Because we did the reverse inverse on times 0 equals n. We know that. But let's do the reverse inverse. What's n times 0? Now this is one we think we know. Because our axiom, or what they call a rule in mathematics, n times 0, because we can break this off. N times 0 does not exactly equal 0. And I gave this the last time on the video, and I'm giving it this time. So now, we're going to let this be this number, okay? It's going to be, since it's an inverse, it'll also be on. Since it's 0, 0, it'll also be on. I started to make this number n. I started to make this number a whole bunch of stuff, but we won't do that. We want to keep math aesthetic and simple and beautiful. You'll see why we just call this number on, just like that number. Because it's the inverse. It's the reverse of that number. And it was undefined. So n times 0 equals undefined. So this is a new number too. Okay? But this will check out. This just checks out. It's like 0 times n is 0, and 0 times 0 is 0, n times 0 is 1. Yep. If you divide n by 0 and get on, then if you multiply n times 0, you should get on. See that? That's called supersymmetry. That's a superposition. That's exactly how that works. So now, then we have the inverse of this number. The inverse here was n times 0, n times 0 times 0, 0 times n. Now this inverse is going to be n times n. So n times n equals n squared. Well, we pretty much know that this should check out. This should check out. This number equals that number. N times n equals n squared. If we have 1 times 1, we will have equal 1 squared. 0 times 0 equals 0 squared. Oh, by the way, could we go up here? Could we do this? Could we do a move like this? -1 times 0. I mean, what? -1 times 1 equals what? It equals -1. But it don't equal 1 squared. It equals -1. So it's an issue right here. Because we should be able to just continue on in squares. 2 times 2 equals, sorry. It equals 4. It does. But that's 2 squared. That's 3 times 3 would be 3 squared. So 0 times 0 would be 0 squared. And then -1. And you might be tempted to do this. -1 times -1. That double sign right there, that negative, that don't go. That don't go. That's not aesthetics. That don't go in mathematics. That's not necessary. That's not a necessary operation to perform mathematics. It's not necessary. So then, when the thing is not necessary and not needed in mathematics, then it becomes obvious that it's just something that people have added in. Now, of course, you could actually do that. You can actually do some mathematics with that. But we are into real mathematics instead, not playing around, not choking. So, I don't even know what I got. But O0. So, that's basically it right there for that part. I just want to show you that this mathematics, it checked out on the alienation, the division level. It checked out on the reverse inverse level, and it checked out on the inverse level. At all points, we have perfect symmetry. We have perfect analytic continuation. We have perfect mathematics. There's no reason why you should still be saying, your computer should be saying that you can't divide by 0. Your computer should read now the new answer. And that's what we're asking you to help us with. We're asking you to help us to allow us to program these numbers and these answers into computers so we can move forward with quantum computers, so we can move forward with, the teaching of our children, the upbringing of humanity, the upliftment of technology, just everything, We would like to be involved in that, and we would like for you to help make that possible. So if you are out there, you see this happen, and you don't see nothing wrong with it, please contact us and let us know what you think, and let us know how you can help us. Because right now we need some many people to come together and help us. And it don't seem like too many people want to do that for us. But we really need y'all to. We really need y'all to come together. Let me get some water right here for 1 second. Okay. Okay. Yeah, so let's see. This is what I was going to show y'all. I'm opening up my phone. Got to put in my little code. I hope y'all saw that. Let me see now. Okay, y'all can check that out. Okay, we're going to get it popping right off the muscle now. So y'all watch. It ain't much, but this is a little video about number 5.
0, that's our friend. Yes, to a mathematician this is a number, but it wasn't always obvious. Math existed to do financial transactions, to sell sheep, to buy copper things, whatever. And you would use coins, and there would be values of the coins. So you would say this costs £5.20 or whatever. You don't do any trading with the number 0. I got no sheep here. Oh, I'm going to buy no sheep. I'll give you no pounds. It doesn't make any sense. So there was no need for shopkeepers to
trying to get a little piece of candy.
They had the idea of 5 cows, but the idea of 5, not so much. The idea of 5ness, they didn't quite understand. So a number like 0, which is the absence of, well, whatever, cows, whatever it was, made no sense to them. I'm going to ask Brady a question, see if I can catch it up. Brady, is 0 an even number?
I think the answer is no, but it feels like it is because it's round.
So this is an interesting. Okay, let me ask you another question. Is 16 an even number?
Yeah.
Yes. So people have studied this. People have a delayed reaction. People are not sure whether 0 is an even number. Now I can tell you that 0 categorically is an even number. It will follow every definition of an even number.
So there was an Indian called Brahmagupta who invented the idea of nothing, not being nothing, but existing as an abstract quantity in the mathematics. Well, then it goes to North Africa, and there's a guy called Al-Khwarizmi, and he writes a book about the art of Hindu mathematics, or reckoning by Hindu mathematics. And that spreads through North Africa to Spain and so forth, and it becomes, they think, Arabic numbers. So you have all the numbers plus 0. That was fine until 1200, when Leonardo of Pisa, also known as Fibonacci, translates this book. It's a wonderful idea, but this is in the period of the Crusades. So people think these are Arabic numbers, not Hindu numbers, because it's come from North Africa. So the Catholic Church objects to this because there are crusades going on, and this is the work of the enemy. So in Florence, for example, they banned the use of this Arabic number 0, and it was thought to be the work of the devil.
Because my definition of an even number is something that can be divided by 2.
So Gray just has told me an even number is a number that can be divided by 2. Well, 0 can be divided by 2. 0 divided by 2 is 0. In fact, in that sense, it is the most even number. In ancient times, they had this idea of things being singly even or doubly even. So 12 would be doubly even when it can be divided by 2, and then 2 again. Well, by that sense, 0 can be divided by 2 and 2 and 2 and 2. It is the most even number. The correct definition of an even number is it is a multiple of 2. Something times 2. Something times 2. When it is, there's no problem with that. It's 0 times 2. Great. Grady said it had to be divisible by 2. Well, that works. 0 divided by 2 is 0. Okay, so it fits between two odd numbers. That might be a definition for even. Let's do that. There's 0, and over here that's 1. Over here that's -1, and then you get 2 over here, -2.
Look at that 1 over 0, y'all.
There are some rules for numbers, some arithmetic rules. 2 even numbers, if you add 2 even numbers together, you get an even number. Well, that works. 0 plus 4 is 4, an even number. Again, that's what we want. We're saying 0 is even. It does every definition. In fact, if it wasn't even, then it would break our rules of arithmetic, which would be a disaster. It is true to say that 0 is neither positive or negative. It sits here between the positive numbers and the negative numbers. So it is neither positive or negative.
The discovery of 0 was the most important advance in mathematics of all, because it made mathematics capable of being understood by everybody. Everybody could do this mathematics.
The Babylonians, the Greeks, they had the idea of space.
Look at the line above.
Between 26, 2 and 6, and 206, 206. They had a space there. They didn't use the symbol 0, but they had a space. It was like more like a punctuation mark. So the Babylonians would understand
Right there, look at that
the
line.
difference between 26
Above.
and 206. But instead of using the symbol for 0, they would just have a space. However, if they wanted to write 260, 260 was written like this, and to us, that looks like 26. To them, and in context, that would make sense. But they didn't have this
In
idea
context,
of
language.
by itself. In the 9th century, the first instance, or the first recorded instance of 0 was found. It was actually found by a gardener, keeping track of the number of flowers that his garden would produce. And he used the number 50 as we would recognize it, 50. After that point, they started to experiment with 0. What could it do? If you add 0, it makes no difference. If you times by 0, you get 0. Dividing by 0, that caused them some problems, as it still does today.
In this sense, the mathematical sense, the number 0 does not mean nothing. quantity which you can manipulate in the mathematics. And so it's better to call it zero rather than nothing. Nothing is when you're counting. There's nothing there. Zero is the abstract mathematical quantity.
I'm CGP Gray, and my favorite number is 0. I like 0 because it's not an obvious number. You can have counting systems where there's 1 thing, 2 things, 3 things, 4 things, but mathematics existed for a long time without having a 0 as part of it. So it's a number, but it also isn't anything in and of itself.
See that? So that's what they're talking about when it comes to mathematics. They don't have no problem telling you that they cannot divide by 0. There's no issue. It's not in your calculator. It's not in your mathematics. It's nowhere to be found. And the fact that we have a way to divide by 0 will not only, like we say, correct that issue, correct the limitations and the errors that in your current calculator, in your current computer, but it'll also correct the mathematicians themselves, like us as people, your children, when you go to school and stuff, they'll have proper mathematics. You see, the guy said, Gray at the end, he said that, you know, mathematics existed a long time without the number 0, without using the number 0. Mathematics went a long time without using the number -1. Mathematics went a long time using the number without using the number square root 2. Mathematics went a long time without using the number I, an imaginary number that has now been defined right here on your number line. Another story on the number I, but nevertheless, you know, that's another new thing. Y'all remember that I'm telling you that the number I, that they call the imaginary number, has been defined. It's already been defined. That's the number. Okay? So they tell you about mathematics, and they tell you that they can't divide by 0, and he's talking about 0 being a number, a nuance number, they call it, an abstract number, they call it, you know, no matter what they call it, they are twisted and tied between whether or not the 0, even if they say, well, in numbers, 0, in numbers, nothing exists in numbers, but 0 exists in mathematics. In either case, that's not a sufficient answer. That's a slick answer, but it's not sufficient. That 0 exists in numbers, but 0 exists in numbers, but the number 0 gonna exist in mathematics. It don't work like that. So you have this number 0 and you cannot define it, and that's the problem. You have this number 1 and you cannot define it, and that's the problem. The number 0 has never been defined, y'all. And the number 1 is still undefined. It's called a pole or a singularity. Look up a pole or a singularity, and you'll see that a pole or a singularity is something that's undefined, something that they can't determine. So the number 0 and the number 1 really don't have an identity on the planet Earth in mathematics until now. Now you know that your identity is moving on. But until now, there was no identity for the numbers 0 and 1. And there was no solution to the problem 0 alienate 0 equals new, and n alienate 0 equals un. There was no answer to that, or 0n. So let me see. There was one other one I wanted to show y'all. Well, there's a lot of them that I really want to show y'all. But let me see. What was it? Let me see. I think I was talking about these folks the other day. That right there, 3 blue and 1 brown. I mentioned that when we talked about the color spectrum. Whoever remember that show, what we did when we talked about that, 3 blue and 1 brown? That's it. That's what I was talking about. So now, let me see. Let me see. Where's this video, y'all? I'm about to get to it. Oh, it's in my Facebook, but I know what to type in YouTube. I got it right here. Math. What was that video? Let's see. Once I know it was on, where's that video at? Man, I'm coming, y'all. Let me see. Okay. Let's see. Just when you want to start going slow. Now, it's this other video called the Riemann hypothesis. I'm gonna show y'all that video because I want y'all to see what the situation is and what's surrounding that video. Like in the Riemann hypothesis, they talk about the Riemann zeta function, and the Riemann zeta function is a function in numbers that they have yet to be able to figure out. It's got a lot of bearing on all other numbers and a lot of other conjectures in numbers. So this is one of them. It's got a lot of bearing on a lot of things in numbers. But this is one of them. This one is short, so it's only 3 minutes. I won't advertise, so y'all can't watch this ad. Okay.
Math wasn't made up to harass English majors. It was invented by a little something called nature, and it's everywhere you look. In fact, there are specific numbers that we see in nature all the time. Together, they're called the Fibonacci sequence, and it goes something like this. 1, 2, 3, 5, 8, 13, 21, 34, 55. Made of this pattern, the first and the second add up to the third, and the second and the third add up to the fourth, and the fourth and the fifth add up to the sixth, so on. The sequence was first described by mathematicians in India about 1,300 years ago, and it was introduced to the West in 1202 Leonardo da Vinci, a.k.a. Fibonacci, who is also responsible for introducing Arabic numerals to Europe, which, if we hadn't done that, we'd still be counting Roman numerals, which would be terrible. Fibonacci was a mathematician, and in his book Liber Abaci, he described this sequence with the thought experiments about a family of incestuous bunnies. If you put one boy bunny and one girl bunny together, that's 2, and those 2 together will make a third, and those 3, when they're done, taking turns, will make 5, etc. The easiest place to find these numbers in nature isn't in bunnies, it's in plants. If you cut a banana into slices, you'll see that it has 3 distinct sections. An apple has 5. No matter what kind of flower you're looking at, chances are it has 3, 5, 8, 13, or 21 petals. Rows of seeds in sunflowers and pine cones always add up to Fibonacci numbers. Now, plants don't grow this way because they're receiving some kind of mysterious cosmic mandate. They're doing it because it's the most efficient way to pack as many seeds as possible into a small space. And if you want to see why that is, you can go watch Vihard's video, which is linked in the description, and it's awesome. But in addition to the numbers themselves, you also see the same ratio between Fibonacci numbers.
Right.
See, when you divide almost any Fibonacci number by the one before it in the sequence, especially the larger ones, you get the same number. 1.618, well, lots of numbers. The Greeks discovered this long before Fibonacci, and they called it phi. Today, it's sometimes known as the golden ratio. Phi was purportedly used by the ancient Greek sculptor Phidias to illustrate the idea of physical perfection. He's said to have used phi as a ratio between a statue's total height and the distance from the bottom of its feet to its navel, for instance, and also the length of a face divided by its feet. There's a whole other set of patterns in nature that are based on what's called the golden rectangle. A rectangle whose side lengths are successive Fibonacci numbers like 8 by 13. This rectangle can be divided up into a series of squares whose lengths are also successive Fibonacci numbers. In this case, 1 by 1, 2 by 2, 3 by 3, 5 by 5, and 8 by 8. When you draw an arc from one corner of each square to the other, they join to form a spiral that resembles many of the spirals we observe in nature. Unfolding leaves of a desert succulent to the arrangement of those pine cone lobes and sunflower seeds and the shells of some snails. Math, you guys. It can be beautiful too. Thanks for watching this episode of SciShow. If you would like to get in touch with us, leave suggestions, ideas, in the comments below, or on Facebook or Twitter. If you want to continue getting smarter with us, you can go to youtube.com/SciShow and subscribe.
Yeah, or you can come to New University TV and learn the truth. So where he was talking about the Fibonacci numbers and that whole thing, we was talking about that. We showed right here that let me cut this off. Okay. Right here, I'm gonna show you right quick. So now, these are some of the most important numbers in mathematics. But you notice that the guy in the video, he told you, he said to y'all, he said, these numbers, he said, flowers don't do that because there's some mandate from the universe. He said flowers do that because they try to pack as many seeds as possible into a tight space, into the tightest space. This is not facts. That's facts. That's what he said. It's not a mandate. So now, these scientists have allowed atheism to creep into science, and that never was. All great scientists that you know, one of them that you can name, and I'll tell you that he knew about the creator, the source, and believe in one. All great mathematicians, name one, and I'll show you that. But society has been fed this atheist thing about science by these new age scientists. I'm telling you, they liars. So now, on that video, it shows you this. See, let me show you this before I write that. When you're dealing with mathematics, you have to be willing to ask questions, though. You can't just go with the flow. That's one thing you can't do in mathematics. In mathematics, that's not the place to go with the flow. That's not the place to just listen. No, mathematics is the place to ask questions. So when he wrote this, or when they put this up, that pen is wet. When they wrote that, 1, and then they said 1, at this point, when they did that, and you didn't see the number 0, 1, you should have been asking questions. You should have been like, where you getting the other 1 from? Where you getting the other 1 from? And then they would have to say, well, we're counting this as 1 square. So then you would say, well, if this is 1 square, is this 0 square? Then they would say, well, you can't have a 0 square in the real world. But we just showed you that 0 times 0 equals 0 square. So you do have a 0 square in the real world. You just have to know its amount. Now, whether 0 square equals 1 square, like this 1 square, if that's two boxes, 1 square by 1 square, right? And that was 2 boxes, 1 and 1. And then if we had another box up here, twice as big, and then we had another box over here, 3 times as big, and then we had another box over here, 5 times as big, like that. And so then we could start our spiral. We could spiral out. We could go around in a spiral. We could come around here, come around here, come around here, go around here, come around here, come around here, like that. We can have, well, I didn't mean to go there, but we can have this big spiral thing going. We have this spiral going. We have this whole spiral thing going around if we want to. So this is how plants, the universe, and everything grows. Now this is just a geometric look at this though. Because at first we were just having a numeric look look at it. 1, 1. So we're going to revisit the numerical look after we get through with this here and we get through with this look. Because he also, when we talk about Fibonacci numbers, yeah, I don't write it that way. I don't even like it that way because I don't like the name really. When we talk about Fibonacci numbers, on the other side of Fibonacci numbers, the inverse of Fibonacci numbers are called phi numbers. Phi numbers. So remember that. It's Fibonacci and phi numbers. Fibonacci and phi numbers. So now, so the question was 0 squared. Is 0 squared equal to 1? So see, we start to look up here, and we can start to make the correlation already between 0 and 1. We have a 0 that's equal to 1 in the space. So we can start to say that 0 times 0 equals something, or 1 times 1 equals something. So we can start to use our number line to sort of see our way through. We not without bearing. We can see the numbers. We can see the numbers. 0 times 0. But once we get this 0 times 0, now we're dealing with a whole new thing. So we can see the numbers. And then we say 1 and 1. We can see the numbers here, 1 and 1. We can see that. We can see that. But both of them ain't even there. But we can see 1 and 1 from here, though. And we could get -1 and -1 here, though. Like we talked about, you wouldn't want to go -1 times -1. It's like not good. It's like not kosher. But in this mathematics up here, you have 2 -1s. You can actually do that. You can actually perform this action without breaking rules. But with the one you have, you only have 1 -1, so it shouldn't be possible because your mathematics wouldn't allow it with the number line you got. Another rule and another way that new mathematics is an addition to your number line, both compatible and compliant to your current number line, but it adds to your number line. So now, let's take this down right quick. So we know the geometric shape of the 1, 1. So then now, let's take this thing out. Let's ask this question too. Greetings, my love. How you doing? Hey, my love. How you doing? Give me a kiss.
You alright?
So, yeah, I'm on, I'm teaching to the air. Okay, I love you, babe. Okay, 1 square and 1 square. So, because if the first one was 1 square, then the second one will have to be 1 square. And so now, where you get 2 1 squares from? Not only are you saying you got 2 1s, but now you say you got 2 1 squares. So now that means you got 1 times 1 and 1 times 1. So where you get the 4 1s from, or the quantum 1, the 4 1s, in order to build that? Or is that the same as 0 1 0 1? Is that the same as 0 1 0 1? Is that the same as that? You see? So you start to see in your mathematics how the number 0 plays a role and it's actually in the numbers. Because it's a square. 0 squared. 1 squared. So it's in here. So now, and another thing that's never said to you is that in order to get to 1 square, watch it. What's after 1 square? Well, 2 squares. But let's not do it like that. Let's do it this way. 1, 4, and then 9 cause 1 times 1 equals 1 squared. 2 times 2 equals 4. 3 times 3 equals 9. So this tells you something about the number 1. When you multiply 2 times 2, you can write 2 squared or 4 squared. Or 4. When you write 3 times 3, you can write 3 squared or 9. When you write 1 times 1, you can write 1 squared or you can write 1. And this begins to tell you something on the scale in numbers, what's actually happening to the identity of number one. It begins to change identity. It begins to change identity. Okay? So now, and so 4 by 4 would be 16, so we could just keep going down with the squares. So all of these numbers would be squares. But when we get to 2 times 2 is 4, and we get to 1 times 1 is 1 square. This is the only one that requires a square every time. This could be 4, 9, like that. But this one would be 1 if you didn't do that. So this is the square. So it's 1 square. But this is not really 1 square. 1 square is really new. I know. 1 square, and all of these numbers, they find the identity in that number new, just like the number I. So now, what did I want to show y'all? So then we got our squares. We got 0, 1, 4, 9. So then let's start with the sequence then. Let's start with the Fibonacci sequence. But let's ask this question though. This other question. They already start us out with 1, 1. And that's 1 square, 1 square. But then they don't include 0. So then our question is, should we include 0? What would be the difference if we said 1 plus 1 equals 2, then what would be the difference if we said 0 plus 1 equals 1? Let's make that 1 square and 1 square. And then 1 plus 1 equals 2. What would be the difference? You got 1 plus 1 equals 2. And if you use 0, you'll have 0 plus 1 equals 1, plus 1 equals 2. So don't you think that somewhere in here that we should count the number 0, that the number 0 just shouldn't be just out of the picture? Because we can't go 1, 0, 1. So if we could do that, then anytime we come up with numbers, it should be including 0. But it's not, because 0 is still undefined, and 1 is still undefined. That's why it doesn't appear. But the thing is that they don't start with 0, they start with 1, and the one they start with is really 1 square, and the other one is 1 square, and they don't tell you where they get the second one from. We can count for the first one there, but we don't know where they get the second one from. And that becomes a problem. They just throw it in, and then they say 2, and then they say 2 plus 1, and then they go on to 3. So that's what we want to do at this point. We want to go ahead and do that. So then it would be 1 plus 1 equals 2, and 2 plus 1 equals 3, and then 3 plus 2, and I don't like the way that's going, so let's do it this way. Let's do it this way. 1 plus 1 equals 2, okay? And then we're going to have to write that 1 there. 2 plus 1, that's going to give us 3. Now, 2 plus 3, right? Or 3 plus 2 is going to give us 5. And 3 plus 5 is going to give us 8. And 5 plus 8 is going to give us 13. You see that? So if we add 1 plus 1, sorry about that. 1 plus 1 is going to give us 2. 1 plus 1 is going to give us 2. 2 plus 1 is going to give us 3. 2 plus 3 is going to give us 5. 3 plus 5 is going to give us 8. So there's 8 plus 5 will give us 13. 5 plus 8, 5 plus 8 will give us 13. 5 plus 3 will give us 8. 2 plus 3 will give us 5. 1 plus 2 will give us 3. And 1 plus 1 will give us 2. And then 0 plus 1 will give us 1. And then we will have to go on. But don't nobody know the secrets how to go on. Don't nobody know how to continue that on. Don't nobody know how to keep going on. Don't nobody know how to say 1 plus 1 of 1 plus 0 equals 1, and then 0 plus whatever equals. Don't nobody know how to continue going on. Except for one person, that's one people, and that's the people that knew mathematics. They know how to keep that going on. They know how to analytically continue that number from here, just like that. Just like that. So, but that ain't to be told tonight. But what we are showing is that we have a 0, 1, a 0, 1, a 1, and a 1, a 1. I mean a 0, 1, a 0, 1, a 1 and a 2, a 1 and a 2, a 2 and a 3, a 2 and a 3, like that. So we have that kind of interplay going. So once we realize that, we realize that, hey, that's very close to what we already have. If we look at these numbers, it's not identical, but it's sort of like our number line. It's sort of like our number line up here. So then we say, well, let's go check it out. Let's go check it out. Let's see if it's like our number line. I think it is, but let's see. Let's check it out. Now, I can't go too deep into one thing though, and that's this. Phi, when it comes to phi, we have mathematics related to that as well as Fibonacci. I'm going to give you the Fibonacci, but regarding phi, it's a couple of things because you'll know that to be true because phi is related to division. Okay, so if you have a Fibonacci 1, 1, 2, 3, 5, 8. Let's say you put a division symbol here, and you say 5 over 8, or 8 over 5. And then you put a division here, say 5 over 3, or 3 alienate 5, or 5 alienate 3. Division 3 alienate 2, or 2 alienate 3. Division symbol, 1 alienate 2, 2 alienate 1. 1 division, 1 alienate, 1 alienate 1. And then, so 0 alienate. You see what I'm saying? And then you will have to go on. You will have to keep going. But this 0 divided by 1 is known to be 0. But this way, 1 divided by 0 happens to be unknown, but it's So at this point, you start having to use your higher forms of mathematics. So that's why I said we're going to erase that right quick, and we ain't going to let nobody see that. Did nobody see that with y'all? Okay? Did nobody see that with y'all? Did nobody see what we just did with y'all? Did nobody see that? Okay, now, so that's relating to phi. So that's why we write Fibonacci like that, because we see that importance to that. Okay, now, but this, how you doing, my love?
Doing great. I'm just watching you.
Thank you. So, I'm about to eat a ginger. I'm hungry.
Oh, yeah? You hungry?
Yeah.
I'm looking for it.
Okay, watch this, hold on. So now, let me see. This is what we're gonna do. We showed this before, and I know people didn't grasp it. But I'm hoping after watching a zero video and watching other videos with us, watching a Fibonacci video, I hope you see how we expounded upon the video that those mathematicians did in the is zero even video. That's on number 5, is zero even video. Go back and watch this video. Watch that video on this channel, and then watch this video again and watch what we did and watch how we expounded on what they taught. Watch. Look how much we expounded on what they taught and how much information that we didn't reveal and we did reveal. The information that we didn't reveal outweighs what we revealed, and we still solved the conundrum for them. We solved the problem for them. We still have more to offer. That's how big the mathematics is. So now, let me show you this. Y'all supposed to thumb the video up. Y'all supposed to show hearts and love and everything for the video. Okay? Now, here we go. Let's just add new plus 0. Oh, sorry. I got my chalkboard line right there, so it don't want to write right there. But I want it to write right there, so I'm gonna make it do it. So that's new. 1 new plus 0 equals new. So what's 0 plus new? New. So what's new plus new? 2 new. That's a new number. You've never seen this number before a day in your life. You've never seen this number before because new plus new equals 2 new. This number is not that number. This number is not that number. This number is some other number because this number is produced from an interaction between this higher plane and this lower plane, producing this number and this number and this number. So this number is 2 new. Oh, we can write this way too. Just to show y'all that, just to give y'all that right there and let y'all know. But that ain't necessary in our numbers. We got this under wrap. We've been through that. Let's go. New plus 0 equals new. And new plus new equals 2 new. And then we'll go new plus 2 equals 3 new. And 3 new plus 2 equals 5 new. And 3 plus 5, 8 new. And 5 plus 8, 13 new. And we can keep going on and on and on and on until infinity. Until we arrive at new again. But the bottom line is what we have just shown is something that has never been shown to anybody in this cycle. Nobody in this cycle, nobody on the planet Earth knew this pattern right here. You could Google this. Go Google the pattern for the Fibonacci number. Go Google the production of Fibonacci numbers. And the only thing you're going to see is 1, 1, 2, 3, and they ain't going to tell you where they come from. They can't tell you where they get 1, 1, 2, 3, 5, 8, where that comes from on the number line. Where that comes from. You got it from nature? Yeah, you got it from nectar, ancient Egypt. Nectar. Nectar. Got it from nectar in ancient Egypt. Because it did get it from nature, and it didn't come from Fibonacci. It didn't come from Algeria. It did. Mathematics was in Algeria, true. His father was a trader, a tradesman, or a merchant man in Algeria, true. From Europe to Algeria, true. However, this dude, Leonardo Fibonacci, or as they call him, Pisano, that's another name for him. Look that up, Pisano. Did not figure out these numbers. When he related these numbers, he gave a story of a rabbit. In ancient Egypt, right now, the symbol of Egypt is the bee. And the bee will reproduce just like this. You have the mother bee, and you have nobody. And she gives, the mother bee gives birth to a daughter bee. And that's 1 plus 1, a son bee. And that's 1 plus 1 is 2. And now, the daughter bee can mate with the son bee and produce 3. And these 2 can produce 5. And these 3 produce 8. And these 5 produce 13. And that's how bees produce right now inside of the hexagon, the honeycomb. Inside of it. Sorry about that, y'all. But y'all get the picture. Inside of the hexagon. Inside of one of them. Bees produce that, and they produce in this number. Now, listen to what I'm telling you now. Bees produce boxes. Bees produce honeycombs. Those are the same thing. These two are the same thing. You see that? Only difference is if I did this like that, or if I did this. And I put them corner to corner. If I put them corner to corner, I'm going to get that. If I don't put them corner to corner, I'm going to get that. So this, and this are the same thing. So bees produce these boxes or honeycombs to hold things in. They produce these boxes. They produce these to hold things in, to hold honey in. Perfect symmetry. But not only do they produce those to live in, to put food in and to live in, but bees also produce this pattern in nature when they reproduce on their own. And there's several other numbers out there that bees fit in a pattern like that. That's amazing, ain't it? That's astounding. That's amazing for the ancient ones, the ancient Egyptians, to recognize that a bee produces in this number, in this order, and that a bee produces this box or hexagon to hold its honey. So a bee became the nectar of nature for all nectar. Nectar. For all nectar. Okay? And it was the symbol of the nectar. The nectar, that means female nectar, a mother nectar. So the mother of God. Nectar, shield. Nectar, mother, shield of God. The goddess of God. The God of God. Mother Nature. Nectar. So this bee, that's part of the indigenous part. But I want you to pay attention to, and this is real easy to say, oh yeah, I saw them talking about Fibonacci numbers on the Nature Channel. They was talking about rabbits. That's about like rabbits and Easter bunnies and having eggs, laying eggs. That's not going to get it. We're talking about our indigenous culture here, and we're showing you that this box, this geometric shape, just like we showed you this geometric shape, we showed you this geometric shape. And this geometric shape is in correlation to these same numbers. And these same numbers are in relation. I didn't mean to say correlation, I meant correlation, but I like saying correlation for a reason. And this is in correlation to that, to these numbers here. Because bees are connected to this, and bees are connected to that. So bees are connected to this, and bees are connected to that. So bees are connected to 5, and bees are connected to Fibonacci, and bees are connected to squares or hexagons. Bees are connected to mathematics. That's why they call it a spelling bee, because it's linguistics, and mathematics is the language. So let's go. Let's do this now. So your children coming to new university, they'll learn this. They'll be taught the magic of the bee. They'll be taught the science of the bee. They'll be taught the science of the square and its relationship to this. They'll be taught pi, its relationship to this. They'll be taught primes, its relationship to this. They'll be taught numbers. They'll be taught the production, the prediction, the position, and the patternization of all numbers in the universe. All numbers in the universe. Every number, all mathematics in the universe, your child can be taught what it is. If you want them to. It's all up to you. You could be taught that. It's all up to you. You could be reminded of it. It's all up to you. Okay, so so now that we have produced a pattern that nobody on the planet Earth has ever produced in no kind of way, and you need to see this. You need to see this in other ways in which we have it. You need to see these same numbers in other ways in which we're able to produce it. It'll blow your mind. Let me show you this though. Okay, so we got this. Got that. Let's see what will happen. What will happen if we went down? 0 plus 1, 1 plus 1, 2, 1 plus 2, 3, 2 plus 3, 5. Wait a minute. Hold on. This is the same pattern. 1, 1, 1, 1, 2, 2, 3, 3, 5, 5. Yeah, let's go. We don't even have to really do nothing because we already know what's coming next. We already know what's coming next. So we say, wow. We say, wow, that's amazing. That is amazing. That's amazing how that just happened. Let's do something else then. Let's say 3 and 2 plus 3 equals 5 and 3 plus 5 equals 8 and 5 plus 8 equals 13. I mean, if you ask me, I think we own something. What you think? If you ask me, I think we own something. Y'all don't think so? I think we definitely own something. I think we definitely got something here. I think we got the patternization and the production and the position for Fibonacci numbers. I think we could predict. I think we could predict the position that this number be in later. I think we could see the patternization. I think we can figure these numbers. The position, the patternization, the production, the prediction, we got it all down pat. So now we can later see on another day, we can see how these numbers will act in a real atmosphere. I'll tell you that. I ain't prepared to do that tonight because I didn't plan on doing something like that this shadow hour. But at a later date, especially in school, because I don't even know if that's appropriate for here. I don't even know if I'll show that on here. But to see these numbers operate in a different plane, that's something that's very beautiful. To see these numbers come off this page and see these numbers operate in another type of fashion. They still on the paper, but I'm just saying in your being, you know where they are. You know they no longer exist on this paper. Just like these numbers don't exist. You can see them on this paper. You can see these numbers on this paper. But you know good and well that these numbers do not exist on this side of hydrogen. It's nothing below 0. What's these numbers below 0? And why are they going up? And are they numbers less than 0? And they must be something because they equal a pattern in nature. All plants, all animals, bees, and everything is attached to this. All universes, all stars, everything, galaxies, everything is attached to these numbers. And attached to that number phi and prime. So what is this? What could those be? Could this be gravity? Could this be the calculation for gravity? And as gravity spread out over a field, is this the weight and the measure and the density? Is this what gravity looks like in a field and a matrix? If we fill in these blanks, if we were to go -1, -3, -5, -7, if we were to go, -2, -5, -8, -11, if we were to just go and fill in these blanks, would we find correlation, like deep type of correlations to like gravity and like forces and energies? Yes, you would. Yes, you would. That's exactly why we're here. That's exactly what new mathematics is. That's exactly why this right here, this material, is just for you. And that's exactly why you should say, hey, they should give that brother and his wife, his family, the Nobel Peace Prize. Because they have worked something out that no scientist and nobody else was able to work out. And they do have new numbers, and they have a lot to add to mathematics, and they deserve funding for their research and development of their mathematics. They shouldn't just sit there and not be respected. I know y'all agree with that. So that's what we're asking y'all for. We're asking for y'all help in that direction. Because you see what we got here, you see what we're dealing with. And we can go on and on and on and on. But we're not. Because BASTET is home. And I think we're about to wrap it up. That's about it. I vibe y'all enjoyed this mathematics. That's right, my love. How you doing?
Yeah, I'm good.
Yes, I'm glad you came over.
Yep. There are a lot of people in the chat.
Yes.
Wow, there's a lot of people in the chat.
Yeah. We can scroll a little bit.
Hey y'all, how y'all
Couple people
doing?
there.
I hope y'all enjoyed the show.
The session, math session.
The math session.
Yeah. But yeah, man.
Hope
So
you took a lot of notes too.
tell them, my love. Tell them we need their help.
Yes, absolutely. We need help. We need help with the funding. We need money, free will offering, because we have a lot of things in store, a lot of projects written out. We need to publish our book.
That's right.
We need to do a professional number line.
That's right.
We just need
A new ruler,
a new ruler,
timetable, addition tables,
yes,
minus tables,
yes,
alienation tables,
that's right.
orders of operation tables, equalization tables,
Yes,
all types of stuff. Fibonacci, 5 prime, pi numbers,
absolutely, yeah.
new numbers, new number lines, new graph lines, new orders of operation, new solutions. Unsolved problems.
That's right. We need a
Just
laboratory.
everything.
We need a laboratory
Yeah.
with just scientists. We need to we need black scientists. We need people to just join us, hop on board and join us in indigenous aesthetic mathematics and linguistics. We need teachers. We need what you call it, a building. We're in the beginning stages. We want indigenous aesthetic mathematics and linguistics to grow.
Yeah.
And you already see the power of numbers. The power that the numbers has had on the three-dimensional world has gotten us out of this planet and into other planets.
Yes.
So can you imagine the room that we have for expansion now with new numbers?
Great point of view. Great question.
We have room for
If
expansion.
we're doing what we're doing now with the first number line, imagine what we could do with both of the number lines.
Yeah, absolutely. So we thank everybody that has made free will offerings so far. We've had 2 people make free will offerings. We thank you, and continue to donate. Continue to donate and help.
And don't forget,
grow.
we're a non-profit organization. So you brothers at the lodge, everybody out there, you sisters in the lodge, y'all help us out. Y'all put together something and help us out as far as what we're doing. We're not asking for money personally at all. We're asking for money to move the mathematics forward. If you want to know what the money is going towards, we'll give you a complete dossier of everything that the money is, down to the penny. If you want to donate, we'll show you every penny of what we spent it on. We have things to get from Fiverr. We need
Computer programmer.
A computer programmer. We need graphic designer. We need a website designer. We need print, like we said, the production of the number line and the designs of that.
Right.
The way the numbers will appear.
Yes.
And different things like that.
Yes. We need worksheets for the children. We need to make worksheets.
Publish the book.
Publish the book. Yeah. So much work to do, and we need your help. We can only.
We're still in the process of becoming a nonprofit because
We're still in the process.
yeah, we got what the fund is. What it is?
We need $850 to file the registration fee.
Yeah, $850 to file the rest of the registration fees. We got everything else. We got the business license, everything. We're incorporated as a business, IAML. Incorporated.
You got the
However, we want to do our nonprofit as Ma'at Cares. And we want to get that out the way and get that situated. And then maybe we can stop asking you guys to help us out so much, because then that'll put us in a position where we can go and ask actual companies and corporations to help us out once we get the nonprofit status. So that's something we're waiting on. We know we could get that on our own, actually. But we asking for y'all help, man. What we gonna do? We're gonna spend all our money doing that, and then what we gonna say? What we gonna eat? What we gonna drink? What we gonna sleep? You know, it becomes a problem, man. Y'all know the deal. Let's be for real. We love y'all, man.
We love y'all.
Peace.
Peace.
We love y'all, goddesses. How we in there? Right there. Yeah.
Is it over? No.
Still in the right there.
Yeah, right there.